Welcome back, guys. I hope you didn't miss me too much. We are on to our last lesson of Math 30-2. Screencastify has saved the day and I'm able to come back just for your final lesson. So we're going to be talking about 6.13 logarithmic scales and applications. Now in this lesson, we're going to actually go through 3 different applications in relation to logarithms. One is earthquakes, then we're going to get into sound levels and pH scale. In all cases, though, we're dealing with the logarithmic scale. So the first one that we're going to talk about is earthquakes. Now, before we get into the examples, in each of these scenarios, I'm going to give you a little bit of background so you understand how the scale works. So with earthquakes, you've probably heard of the Richter scale before, and the Richter scale is used to measure the magnitude of an earthquake. And that's the magnitude of an earthquake is essentially the measure of the amount of energy released. Now, the Richter scale itself is logarithmic, and so a difference of 1 unit in magnitude corresponds to a factor of 10 difference in intensity. So if in the media you're hearing about a magnitude 8 earthquake, that's 10 times as intense as a magnitude 7 earthquake. And a magnitude 8 earthquake would be 100 times as intense as a magnitude 6 earthquake. Now, if you were to hear about a magnitude 1 earthquake or a magnitude 1 on the Richter scale, that's equivalent to a large blast at a construction site, and it's 10 times as intense as the 0 reference point used for the scale. So when we talk about the intensity of an earthquake, we can calculate this using a formula. Now, if we were going to be writing the diploma here, you would see this formula quite frequently on the formula sheet on a diploma. Sorry, not on the formula sheet, but on the exam. So they would use I equals IO 10 to the M. Often you'll see me write it this way: I over IO equals 10 to the M. Now, I represents our intensity of an earthquake, and M is the magnitude of the earthquake on the Richter scale. IO is our initial intensity, or the intensity of an earthquake with a magnitude of 0. This other formula here we use quite frequently as well. The intensity of 2 earthquakes can be compared, and we go I over IO equals 10 to the M1 minus M2. And so if we take the intensity of the first earthquake and divide by the intensity of the second earthquake, that ratio will be equivalent to 10 to the magnitude 1 minus magnitude 2. All right, so if M1 is 4 times as intense as M2, then M2 is 1/4 as time, or 1/4 times as intense as M1. So if M1 is bigger than M2 by 4, or 4 times greater, that means M2 is 4 times smaller than M1, or 1/4 times bigger. If the ratio between I over I2 is greater than 1. So if I were to take M1 and divide by M2 and I get an answer of 4, then M1 is bigger than M2. If, however, I take I1 over I2 and my answer is between 0 and 1, then M1 is smaller than M2. So if I took the intensity of M2, or if I took the intensity of M2 and said it was 1 and divided by the intensity of M1, which is 4, if I got 1 over 4, that's a value between 0 and 1. So that tells me that the magnitude 1 is less than magnitude 2. All right, so it's just important for you to understand that, so that when you get an answer, if your I1 over I2 is bigger than 1, then you know that M1 is bigger. If you get a value that's between 0 and 1, then you know that your M2, or the magnitude of that first earthquake, is smaller. All right, let's take a look at the actual Richter scale. So an earthquake of magnitude 5, remember that every time we move from a 5 to a 4 to a 3, we're changing intensity by 10 times. An earthquake of magnitude 5 is blank times as intense as an earthquake of magnitude 4. Well, if we're moving from magnitude 5 to magnitude 4, 5 is bigger and it's 10 times bigger. Now, an earthquake of magnitude 9 is blank times as intense as an earthquake of magnitude 5. Well, if I jump from 9 to 5, that's a jump of 10, another jump of 10, so 100, 1,000, and another 10 would make it 10,000. So it's actually 10 to the 4 jumps, which is 10,000 times. So an earthquake of magnitude 9 is 10,000 times as intense as a magnitude 5. Now, an earthquake of magnitude 6 is blank times as intense as a magnitude 8. Well, notice that 6 is smaller than 8, so we're going backwards. We're going dividing by 10, or 10 to the negative 2. We can also represent that as 1 over 100. So it's 100 times less intense. An earthquake of magnitude 3.8 is blank times as intense as an earthquake of magnitude 5.8. Well, 5.8 minus 3.8 is 2, so this is also 10 to the 2, or 1 over 100 times as intense. Now, taking a look at some specific examples here, the 1960 earthquake in Chile was blank times as intense as the 1976 earthquake in Italy, and blank times as intense as the 1983 earthquake in Colombia. So first of all, let's take a look at the 1960 earthquake in Chile, registered 9.5 on the Richter scale. And then the 1976 earthquake in Italy, 1976 registered as 6.5. And the 1983 earthquake in Colombia registered as 5.5. So 9.5 minus 6.5 is 1,000. So it was 1,000 times as intense as the 1976 earthquake. 9.5 minus 5.5 is 4. So this was 10 to the 4, or 10,000 times as intense as the earthquake in Colombia. Now, in 1966, there was an earthquake in Turkey, and that registered 6.9 on the Richter scale. And we had an earthquake in Japan in 1933, and that one registered 8.9. Well, the Turkey earthquake was less intense than the Japan earthquake, so 6.9 minus 8.9 is -2, so it was 10 to the -2 times as intense, or 1 over 100 times as intense. All right, so let's take a look at some specific examples. So the first question we're asked here is to explain why an earthquake with a magnitude of 8.5 is approximately 40 times as intense as an earthquake with a magnitude of 6.9. Well, we're going to use this formula here. The I1 over I2 equals 10 to the M1 minus M2. So we're looking for the intensity. And we're told that the magnitude of the first earthquake is 8.5, so 8.5 minus 6.9. So I1 over I2 equals 10 to the 1.6. And if we put 10 to the 1.6 in our calculators, we get 39.8, which is approximately 40 times as intense. All right, now we can't always just use our numbers on the Richter scale because not everything's going to be perfect, perfect factors of 10 or bases of 10. So we're going to have to do some calculations with logarithms. So example number 3 here, it says a major earthquake of magnitude 7.5 is 375 times as intense as a minor earthquake. Now the question says, is the magnitude of the minor earthquake greater or smaller than 7.5? Well, given that the question says major and minor, we can probably assume that the minor earthquake is smaller than the major earthquake. However, we can also figure this out using our calculations or using our numbers. So we're told that the magnitude 7.5 earthquake is 375 times as intense as a minor earthquake. That means that our intensity of I1 over I2 is going to be greater than 1. So that means that M1 is definitely bigger than M2. And so that means M2 is smaller than M1. Now we're going to use the formula here to determine the magnitude of the minor earthquake. So we're told that the intensity of M1 over M2 is 375 times as intense. So that means our I1 over our I2, even though those are two different variables, the ratio of those represents our 375. So using our formula, we're going to have 375 equals 10 to the 7.5 minus x. Solving this, we're going to rewrite it as a logarithm. So log base 10 of 375 equals 7.5 minus x. Solving, we're going to have x equals 7.5 minus log base 10. And we don't have to write the log base 10. We can just write log of 375. and x equals 4.9. All right, moving on, we're going to take a look at the sound scale. Now, when we start looking at the decibel scale, this follows the exact same rules as the Richter scale, but we're still going to go through some examples. So the loudness of sound was originally named bells, and it was named after Alexander Graham Bell. The current unit that we use, though, for sound is decibels, and decibels are 1/10 of a bell. So if I want to convert from decibels to bells, I have to divide by 10. So similar to the Richter scale, the Bell scale is logarithmic, and a difference of 1 bell or 10 decibels corresponds to a factor of 10 difference in sound intensity. All right, so a leaf rustling. A leaf rustling would register at about 10 decibels or 1 bell, is 10 times as intense as the threshold of hearing. And a whisper, 30 decibels or 3 bells, is 10 to the 3 or 1,000 times as intense as the threshold of hearing, and 10 squared or 100 times as intense as a leaf rustling. All right, now if we want to compare sound intensities, we have these two formulas. The loudness of sound can be measured in decibels or bells. So bells would be equal to log of I over IO, and decibels would be 10 times log of I over IO. Another formula that you'll see, and it looks very similar to the one that we did with the earthquakes, the intensity of two sounds can be compared. It would be I1 over I2 equals 10 to the bell 1 minus bell 2. Now notice that these are bells, not decibels. All right, so let's take a look at the scale here. So a power saw at 120 decibels is blank times as intense as a telephone dial tone of 80 decibels. Well, 12 or 120 decibels, remember, is 12 bells. 80 decibels is 8 bells. 12 minus 8 is 4. So that means it's 10 to the 4 times as intense, or 10,000 times as intense. A jet engine at 20 meters is 145 decibels, and that's blank times as intense as the threshold of pain. Well, if we take a look, the threshold of pain is at 125. And so 14.5 minus 12.5 is 2. So it's going to be 10 squared is times as intense, or 100 times as intense. And the third one here, it says a whisper of 30 decibels is blank times as intense as a conversation of 60 decibels. Notice that 30 is smaller, so this is going to be 10 to the negative 3, or 1 over 1,000 times as intense. All right, taking a look at an example here, we're asked how many times more intense is the sound of a piano playing at 67 decibels than a whisper of 22 decibels. So we're going to use our formula. I1 over I2 equals 10 to the bell 1 minus bell 2. So we have our intensity is what we're looking for. So I1 over I2 equals 10. Now, if our decibels are 67 decibels, our bells are 6.7. So 6.7 minus 22 would be 2.2. That gives us 10 to the 4.5. And if we compute that, we get 31,623 times as intense. So the sound of a piano playing is 31,623 times as intense as the sound of a whisper. Now, example number 6, if we're given decibels equals 10 log I over IO, we're asked to show that the decibel level for the threshold of pain, 125 decibels, has a sound intensity of 10 to the 12.5 IO. Essentially, we're asked to take our formula and rearrange it. And so our decibels are 125, so we're going to plug in 125 equals 10 log I over IO. Now, to get our logarithm by itself, we have to divide by 10. 125 divided by 10 is 12.5, and that's going to give us log of I over IO. Now remember that there is a little 10 that's written there, we just don't see it, so we can rewrite this as an exponential function, and so we can rewrite it as 10 to the 12.5 equals I over IO. We're being asked to solve for intensity, So we're going to rearrange the equation, set it equal to I. I is going to equal 10 to the 12.5 times IO. Now this could also be done using a left side, right side chart. Today I just chose to plug in the values and reduce until we got to the final answer. All right, we're going to take a look at one more scale, and this is the pH scale. Now the pH scale is also based on a logarithmic scale, and pH scale measures the range of hydrogen ion concentration by determining the acidity or the alkalinity of a solution. Now, pH values that are right at 7 are considered neutral. And so anything that goes above 7 becomes more alkaline, and anything that goes below 7 becomes more acidic. And so again, 7 is our neutral level. Now, similar to the Richter scale, the pH scale is logarithmic, and a difference of 1 unit of pH corresponds to a factor of 10 difference in intensity. So if vinegar has a pH of 3, then it is 10 times as acidic as tomato juice. So tomato juice would be at 4. Since 3 is more acidic than 4, pH of 3 is 10 times as acidic as 4. Household ammonia at a pH of 11.5 is 10 times as alkaline as milk of magnesia, which is a pH of 10.5. So notice as we get bigger with our numbers, we become more alkaline. So 11.5 is bigger than 10.5, so it's more alkaline. Or we could say that milk of magnesia is 10 times more acidic than household ammonia. Or we could say that milk of magnesia is 1 over 10 times more alkaline. All right, so we're going to take a look at our scale here again. So looking at our pH scale, we're asked to compare the values. So tomato juice is blank times as acidic as pure water. So tomato juice is at 4 and pure water is at 7. And we're going, as we go up the scale here, we become more acidic. And so 7 take away 4 is 3. And since it's becoming more acidic, it's 10 to the 3 times as acidic as pure water, or 1,000 times more acidic. Eggs are blank times as alkaline as pure water. Well, if we take a look at eggs, eggs are at 8. Pure water is at 7. And we're talking about becoming more alkaline. So as we go further down the list here, it becomes more alkaline. So eggs are 10 times as alkaline as pure water. Now, eggs are blank times as acidic as pure water. Well, if we're talking about going from 7 to 8 becoming more alkaline, but the question is asking us about acidic, it's actually 10 to the negative 1, or 1 over 10 times as acidic. Milk of magnesia is 1,000 times as intense as blank, or sorry, 1,000 times as blank as blood. So the question is it more acidic or is it more alkaline based on the 1,000 times? So if we're going to look at milk of magnesia, that's at 10.5, and we want to take a look at blood at 7.5. As we go up the scale, it becomes more alkaline. So this number is greater than 1. So 10.5 minus 7.5 is 3. So 10 to the 3 is 1,000. So it's more alkaline. And blank is 100 times as acidic as normal rain. Well, we're going to look at normal rain is at 5. And if it's 100 times as acidic, we need to be moving more to the acidic. And if we take a look up, 100 times is 10 squared. So 2 jumps up takes us to vinegar. So vinegar is 1,000 times, or sorry, 100 times as acidic as normal rain. And our last question, eggs seem to be popular today. Eggs are 1 over 10,000 times as alkaline as blank. So we're looking at eggs. Eggs are at 8. 1 over 10,000 means 1 over 10 to the 4. So we're looking for a jump of 4. 1, 2, 3. So we look for 4. So it's either going to be tomato juice or it's going to be washing soda. But it says 1 over 10,000 times as alkaline. As we move down the scale, these items become more alkaline. So if eggs is the reciprocal, 1 over 10 to the 4, then we want to find something that actually is becoming more alkaline, because eggs would be less alkaline than that. And so the answer is washing soda. All right, so we do have a couple formulas here for pH as well. All right, so we have a couple formulas here. The first one we've been using already. If we want to find out how much more acidic or alkaline one solution is than another, we can use 10 to the pH1 minus pH2. But this formula down here is the one that you will often see more commonly in 30-2. So the pH of a solution is defined as pH equals negative log of H positive. And H positive is the hydrogen ion concentration, and the units are moles per liter. Now, if you took Chemistry 30, you've seen this formula, you've used it probably a few times. So let's take a look at a couple examples here. Example number 9 says a patient gave a urine sample which was found to have a pH of 4.7, and we're asked what the hydrogen ion concentration was, and we're going to answer in scientific notation using 1 decimal place. Well, our formula is pH equals negative log of H positive. Our pH is 4.7. And that equals negative log of H positive. And remember, there's log base 10 there. We just don't have the 10 written. Our first step is to divide by negative 1. So we're going to have negative 4.7 equals log of H positive. And rewriting that as an exponent, remember that there is a 10 there. Rewriting this as an exponent, we have 10 to the negative 4.7 equals H positive. Writing that as scientific notation, on our calculator, we're going to have 1.995 times 10 to the negative 5. However, we're asked to round to 1 decimal place. So then the 9 will round up the 9, which will round up the 1. So going to 1 decimal place, we're going to have 2.0 times 10 to the negative 5 moles per liter. And the reverse of that would be if we were given the hydrogen ion concentration and we're asked for the pH. This one we might not see as commonly. Typically, we're in 30-2, you're going to be expected to do some sort of manipulation of the equation, but you could be asked this question as well. Determine the pH of a solution to the nearest tenth if the hydrogen ion concentration is 3.8 times 10 to the negative 4. So again, we're using that formula, pH equals negative log of H positive. And we're looking for pH. So equals negative log of our hydrogen ion concentration, which is 3.8 times 10 to the negative 4. Now on your calculator, you can write that as 3.8 times 10 exponent negative 4, or you can type 3.8 and then you can do second function e, which is right above your comma. So you could go 3.8 second function, comma, you're looking for the EE that's right above that, and then type negative 4. So on your calculator, it'll look like this, 3.8 E negative 4, and that would mean the same thing. So we type that in, pH equals negative log of 3.8 times 10 to the negative 4, and we get a pH level of 3.4. And that is our last example of our last lesson of our COVID-19 Math 30-2 lessons. I can't believe we've been doing this for 3 months, and I can't believe that it's coming to a close. I cannot wait to see you guys in person, hopefully sooner than later. And I just want to say thank you guys for sticking it out with me. This has definitely been an experience, and it's something that we're probably going to talk about for years to come, but I just want you guys to know how much I appreciate you and how much I miss you, and we'll see you soon.